Hello everyone, we are group number 5, formed by Daniela Rosada, Andres Guerrero, Daniel Cabrera, and Julian Moreno. We are going to present the design and simulation of a centrifugal pump. First, it's crucial to contextualize you a little bit. Centrifugal pumps are known as rotodynamic pumps. These pumps raise the pressure of a liquid by imparting velocity energy and converting it to pressure energy. These pumps are used in different industries, like the chemical industry, petroleum industry, construction, among others. The design of these pumps is divided into two parts: impeller and pump casing. There are three types of impellers: closed, semi-open, and open. The main objective is to design and simulate a centrifugal pump. For the simulation, computational fluid dynamics (CFD) will be used because it helps to reduce experimental costs and prevents possible errors due to the pump's design. It's vital to highlight that the geometry design will be based on the water properties and the angular velocity of 3,550 revolutions per minute. Considering and using Gulick's method equations, we can calculate some points that will help us to graph a two-dimensional meridional and radial view of the impeller, the number and distributions of the impeller's blades, and the pump casing. You can appreciate all these views in this slide.
After making the geometry design calculations, Autodesk Inventor is used to create a 3D CAD. First, the impeller is created. Data is imported to the program and using tools such as extrusion, revolution, and others, the impeller can be created. It is important to establish that the impeller's creation is critical because it will affect the pump's performance. Also, the impeller created on Inventor will be semi-open because this helps to eliminate some friction, making the pump more efficient. The pump casing is then created. Important tools that required in this creation are elevation and extrusion between planes. During the creation of the casing, it is important to take care of some dead zones that could create high stress. Finally, an ensemble must be created by the combination of the impeller and the casing. The isometric planes of the pump created in Autodesk Inventor are shown in this slide. After creating the CAD on Inventor, it is important to establish the mesh models. Firstly, polyhedral meshes. As the pump has a complicated geometry, a polyhedral mesh is required to maximize the curved zones. This unstructured mesh has a better simulation if the number of vertices increases. Also, the polyhedral mesh leads to a quicker convergence of the numerical solution. Some parameters are required for creating this mesh: base size of 4.62 mm and the minimum surface size of 0.5 mm. Secondly, the Prim's layer measure. This one is used to generate a high quality boundary layer mesh at all surface concerned. The number of Prim's layers used in this simulation will be 4 and the Prim's layer total thickness will be 0.5 mm. To prove that the mesh created is the most efficient, it is necessary to make an independent mesh comparison between the mesh created and two new meshes with different base size, one with minus 30% of the original base size and the other with plus 30% of the original base size. In the table shown, you can see the comparison. It shows that when the base size is bigger than the preset mesh, the number of cells decreases, which is good because it requires less time of iteration, but the pressure drop increases. When the base size is shorter, the opposite happens. Consequently, it is preferred to use the preset mesh for future simulations because it has an average number of cells and require an average time of iteration.
First, Reynolds must be calculated to correctly choose the physical models. As shown in the slide, the water and mineral oil values are in turbulent regime. Therefore, the chi-epsilon turbulence model can be used. This model considers the turbulent kinetic energy and the turbulent energy dissipation of the unknown variables. It will also be assumed that the system does not change in time. It means it is steady. The fluids are liquids with constant density, so that it will apply a segregated flow model. It means that water and hydrocarbon phases can be effectively treated as taking different flow paths to the hydrofracture network. The wall Y plus can operate in three layers: viscous sublayer, buffer layer, and lock-low layer. In the viscous sublayer, the viscous effect dominates. The buffer is the transition between the viscous to the lock-low, and lock-low is when the turbulent sublayer dominates. To simulate, it's more effective to have Y plus values in the viscous sublayer, because the prediction is more accurate and the time is not a critical issue. When the mesh was created, it had a few problems. Some were that the mesh did not create cells in critical places for certain base sizes. Therefore, the value of worldwide plus for water was approximately 27.98, and mineral oil was approximately 1.43. Therefore, the Y plus of water is in a buffer layer. It means that the accuracy of the simulation iteration will be affected such that the result could be imprecise. The figure shown can be appreciated by comparing the head, efficiency, and power of the simulations with water, mineral oil, and the fabricant data, with different flow rates. On the first hand, the head decreases as the flow rate increases. Also, as is shown, the fabricant data head is higher than the water and oil simulations because the housing could cause friction. On the other hand, the power needed for the water is bigger than the one needed for the mineral oil. This happens because the water is more turbulent than the oil, so the pump requires more force to push the fluid out of it. Finally, according to the fabricant data, the efficiency must be approximately 0.7. point 0.7. Nevertheless, the efficiency after the simulations was 0.54 and 0.43 for water and mineral oil, respectively. This decrease can be caused by design problems that generate losses for friction or dead spaces between the ensemble parts. It can be concluded that the pump is more effective for fluids like water than oils due to the viscosity and turbulence of these. After comparing this graph, it is important to make a polynomial regression to find a flow rate for both fluids and make a proper analysis of the pump's velocity and pressure. The flow rates found were 172.5 meters cubic per hour and 160 meters cubic per hour for water and mineral oil, respectively. The following scene was created. It can be seen that the magnitude of the velocity is bigger from the inlet and then decreases at the outlet, which indicates that the fluid has been pumped correctly.
Then, as seen for the impellers, velocity was created, and it can be appreciated that the velocity magnitude for both fluids at the impeller is the same. The fluid enters from the impeller's top phase, water crashes with it, and creates some dead zones that will affect the pump's efficiency. Furthermore, it can be said that the impeller is rotating correctly, so the fluid can be pumped as expected. On the other hand, it is crucial to verify if the pump's design presents cavitation. Cavitation refers to the formation of voids or hollows within a liquid medium. If the fluid saturation pressure is between the range of absolute total pressure, bubbles could be formed and some of the fluid can be evaporated. This damages the pump quickly. The vapor pressure of mineral oil is approximately 0.6 MPa and for water is 1.8131 MPa at a temperature of 15 Celsius degrees. As it can be seen in figure 6, the range of pressure for mineral oil is between minus 1.932 MPa and 1.808 MPa, and for water is between minus 2.793 MPa and 2.162 MPa. It indicates that the pump presents cavitation for both fluids, so they will evaporate and create bubbles inside the pump. The negative pressure reports imply failures on the mesh and in the simulation, so although this imprecision, those reports were taken as potential cavitation zones. Finally, it can be said that the pump had higher efficiency with water than with oil. The pump presented some cavitation zones. The pump did not adjust properly to the fabricant curve. Despite of this, both curves had the same behavior for both fluids. The use of programs such as Inventor and StarCMM Plus was highly beneficial for approaching a real-life behavior of a pump. And for future research, we recommend to pay attention to the variables that could decrease wall-wide loss and to try to prevent cavitation zones, increasing the pressure inside the pump and improving the mesh. That's all for now. Thank you all for watching and listening, and have a good day.